Hello, everybody, and welcome to the HAO Colloquium. And today we're very happy to have Dipankar Banerjee. And Dipankar is currently the director of the Aryabhata Research Institute of Observational Sciences, or ARIES, in Nainital, India. He's also the co-chair of the Science Working Group for the Aditya mission, which is the first dedicated Indian mission to study the sun. It's expected to be launched by ISRO, the Indian Space Agency, in 2023. Dipankar is also the project coordinator for the National Large Solar Telescope Project, or NLST, which is a proposed 2-meter ground-based telescope planned to be installed at a Himalayan site. He's involved with Punch, the NASA's Punch mission, and is an honorary fellow of the Indian Academy of Sciences and the National Science Academy, and currently the president of the Astronomical Society of India. And today, Dipankar is going to be talking about long-term study of the sun using Kodaikanal and other digitized data archives. Welcome, Dipankar.
Thank you very much, Sarah. It has been always a pleasure to visit HAO. So today, I thought, I will give you an overview of the current status of this Kodaikanal archive. And we have been involved with the digitization process of this Kodaikanal, data, and I will highlight the salient, extra features of the Kodaikanal archive as compared to other data archive. So I will come back to this slide because this is the, composite sunspot area series combining data from 18 different observatories across the globe. So we have now reached a stage probably where we should not only look at individual data archive, but from the composite series. So it's very important to prepare this composite series with a lot of care because you need to know the differences between the different series, what are the sources, why they're different, and then if you can cross-calibrate them to bring them into the same platform, and then make these series available to the larger community. Before I do that, I will take you a little tour of the location where I come from. So this is a beautiful hill called Nainital, and that's my office here. This used to be called UP State Observatory, and more than 50 years back, this little telescope, it's a 1-meter class telescope, which was installed here, and still it is fully functional. And our PhD students, I often refer to this as our PhD students' toy, because it's only the PhD students who get a chance to observe with this. Of course, we have much bigger facility now. Primarily, this is a nighttime, observatory. Also, it has atmospheric science facilities, particularly stratosphere and troposphere. We have STSW, LIDAR, and other atmospheric chemistry measurements in terms of ozone and other chemistry in the lower atmospheres. I will not talk about it, but I thought, since I'm here, just to give you an insight about where I come from. And this is our new, observing facilities in a location of 2.5 kilometer altitude. This is one of the best sites within the country now, apart from the Ladakh region, which also hosts a 2-meter class telescope. But interestingly, this particular site, and as you can see, it's a unique facility because we have a state-of-the-art with the active optics capability of the primary 3.6 meter, along with a 4-meter liquid mirror telescope. Nowhere else in the globe, actually, such a liquid mirror telescope exists for astronomical observations today. And again, in the same location, we have a 1.3 meter DFM telescope. This is again our students' toy, because mostly the students, use this facility. Interestingly, as I mentioned, that the liquid mirror telescope is a sort of a ball containing mercury, and the ball is rotated at a uniform speed to build this, primary mirror surface. And in the secondary, you have a direct CCD camera. Of course, this camera needs to operate in a very specific mode called TDI mode, time delay mode, so that it can take care of the trail of any objects. The interesting thing is that it is always looking at a 20 square degree of the sky, because the mirror cannot be turned, this way or that way. So always it is looking at the zenith with a fixed, field of view. And within that field of view, any object comes, whether it is a star, whether it is a comet or a debris or a extragalactic source or a gamma ray burst, everything is captured. So you have 1 million of objects in each frame. So the beauty is that now you have to have a very good data pipeline. You have to have, catalogs to identify anything new in this if every frame. And also the idea is if you can identify, suppose you identify a gamma ray burst, and then next door you have a 3.6 meter telescope with the back end, high resolution spectrographs with infrared imagers and so on. So you do the characterization of that object with much better, precision. At the same time, having a combination of this kind of, transient detection, facility along with a very reasonable, modest class dedicated back-end, instruments allows you for a characterization of these kinds of transients very well. So this is, I think, going to make a real big change. And the other thing is we are able to motivate a lot of youngsters to look at this data, because as I indicated that this, you have millions of objects, and AI ML is the perfect, application for this kind of, transient identification and follow-ups. Eventually, the plan is basically with SDSS, what people have achieved for a good sky survey. So this 5-year full operation will allow you to do a new catalog with lots of hopefully new objects with a better photometric, calibrations and so on. So there is astrometry, there is photometry, quite a bit of, image processing, details are required for making this particular data to be, very, very useful. So I think it has a lot of potential in terms of, bringing. These are the two pictures from the same site. Actually, it's been taken one by Vibhuti, one by Ritesh here. They're here, so I can't in fact, the irony is that they moved from Bangalore with me when I took up this directorship in this Himalayas. And there were pandemic period. So they picked up this astrophotography skill set during their tenure. So for submission of their thesis, they had something else also to pick up. So the point is, it's a beautiful site. It's a pleasure to work in this environment. So that's a very brief tour of the place where I'm coming from. But now I will take you down to our Kodaikanal Observatory. What I would again emphasize today is that this observatory is probably the only place where we have multi-wavelength data sources for the past 100 years. Because majority of the other observatories, either whether you call it, any Greenwich or any European or American sites, typically they're known for one data series, either it's a calcium or it's a, white light, or if you go to MEDO, the H alpha. But here is one location, same day you have often, all the 3 wavelengths recorded. And that makes it quite a unique thing also for consistency purposes as well. I will elaborate on that. So this is a typical example. If you go to the archive and look at 1st January 1958, you will find, all the 4 data series. So you have white light, you have calcium, you have H alpha, and then also we have another data source called prominence plates. Basically, it's blocking the solar disk, as you see here. And in calcium, these prominences have been recorded, and this is quite unique. There are not many places this data exists, and all these data are in the public domain. I must point out that I'm very happy to note now that the calibration of these data is very critical for really doing the interpretation. And since we could make this data public, the raw data in the FITS format with 16-bit and all that was distributed across. There are Japanese teams, there are Russians, there are Europeans, there are Americans. They have all their own methods have been applied, and now we are trying to collate all these and trying to make these composite series as well. So this is, I think, was very much required across, and I'm very happy. Apart from this, just a few of our groups output we have shown here. Again, highlighting the span of the data, if I now focus on this sunspot on the top, I mean, basically the white light data, as you see here, typically the number of, observing days is, about 75% of the duty cycle, I would say, because of the weather and all that. Kodaikanal is in the hill station, so it does get affected by monsoon. And this is the calcium K. Some days you have, 2 or 3 observing plates available. So that's why the number of observations are more, but number of observing days is always, between 230 to 250. This is calcium K prominence, again, a very similar trend. I would also point out that beyond 1980s, the quality of the data and quality of observation from Kodaikanal has been a major issue with more tourists coming in and the weather pattern changing and all that. It is indeed that we find, the quality of the data is poor. Contrary to the belief that the older the data, we have better quality of, images. That also clearly goes to the people who have preserved the photographic plates, because it's not easy to maintain those photographic plates in the very wet conditions at the Himalayas. This is not Himalaya. This is one of the hills in the south, though. This is again H alpha series, what you see. But the lowest, panel depicts the number of observing days where all 4, plates are available. I think that makes the Kodaikanal quite a unique thing, because I will bring to this that now we are trying to reproduce the magnetic cycle, which needs calcium, which needs H alpha observations more or less same simultaneous time, because calcium is giving the proxy of the magnetic field concentrations, and H alpha is showing us the locations of the neutral lines. Combining these 2 informations, we are able to get a magnetic pseudo-magnetogram, so to say. So I will show some examples of that. There is also another interesting aspect is the sun charts, and I think sun charts have been getting digitized across in different locations. And the beauty of the sun charts is that they are not affected by weather conditions, more or less, I would say. In terms of really, we have photographic plates which are not in good condition, of the films which are not in good condition. But we are seeing very clearly that the sun charts have a better duty cycle. So we, whenever there has been observation, because the sun charts were prepared more or less in the same time, all along, it's not that the post facto it was made. So, they're still there. So if we just use the sun chart, as you can see, it is often 300. Some days, sometimes it is 300 plus as well. So we have some data gaps we may be able to fill by, extracting the data, resources from the sun charts as well. So this is again an important resource. I will also like to point out that initially when we digitized them and we did one set of results and all that, and then we discovered more and more problems. Particularly for certain periods, sometimes, because of certain issues with the instruments at certain phases. And we're trying to improve the series as well. So here I will just give you a very quick update of sunspot area series. So the first result was published a few years back, and we could only do for this period. And there were issues for this with the calibration, primarily with also the orientations and so on. And I will just show you briefly where we have changed these things. And again, highlighting the coverage of, Kodaikanal here. So here what you see, this is the span of Kodaikanal, more than 100 years of data, actually 114 years of data from. One must also point out that RGO series extends for 103 years, but RGO is not from RGO only. RGO has taken plates from many locations, including Kodaikanal. So they did some, manual, I would say, cross calibrations in those times. So when you look at RGO series, it actually has data from other observatories also. But having said that, of course, that goes to the oldest period. So RGO has to be taken as a calibrator for when we do the composite series and so on. So this is the recent result, which Vibhuti, who is here in this audience, with the new Kodaikanal sunspot area series. What we are also highlighting that we are now looking at not all the sunspots at the same merit. We are particularly looking at area-wise segregations. The question is whether the small sunspots are behaving the same way as the big ones. I will not have time today about in recent work which one of our students with Vidya is doing. Anu's work probably you have some of it. We are able to now track each of these sunspot pair, because in this kind of analysis or this kind of area series, you see these each bipolar magnetic regions have been often been counted more than once, because we are always looking at the same. No bipolar regions have been really tracked. Their lifetime has not been accounted when this kind of cities have been produced. And that doesn't allow us to really study the temporal evolution of the bipolar magnetic regions. So this is a very detailed work which one of our students is doing, but I will not be presenting it today. I presented it in the morning in the ILWS. But if people are interested here, we can talk about it later on. So that's a sort of sunspot area thing from Kodaikanal add-on. But this is, I was mentioning that this is probably the state-of-the-art sunspot area catalog, which is available, which was done by my former student who is now in Max Planck. So Sami's group had access to sunspot areas or the data, actually, the images from all across the globe. So it was important to cross-calibrate them and then put them into one level. As I said, there's scaling required when we do compare with RGOs, because each site has taken images with certain instruments, certain pass bands, and so on. Of course, white light doesn't get that much affected, but for the case of the calcium, it is very, very important, and that has been now being addressed very particularly. This is again showing how the small guys, which is indicated by these blue ones, and the red fellows, which are the biggest fellows, how they appear at what latitude and what phase of the solar cycle and all that. Very clearly it shows that the biggest sunspots always come into the maximum period, and they are mostly appear in much lower latitude, whereas the smaller ones are really appearing throughout the solar cycle all along, and they have a higher latitude distribution. Now, always the question comes to whether the small sunspots, they are coming from the same global dynamo or they are a local dynamo. So this is a question which also demands that these small sunspots are looked at more carefully, their lifetime, their appearance, disappearance, and the migrations within different latitude bands and so on. So this is the work which we are doing, and it demands much more details. Here today, I'm just giving an overview of most of the archival current status and how we are involved in improving it. This is a paper which a couple of years back, again, Theo led this. Basically, what we were looking at, so there was an 8-bit earlier scanned images of Kodaikanal, which was available globally, particularly with Sami and then Alexei and so on. And earlier work was done mostly from those 8-bit JPEG images. But when we had the new digitization program, we had a 4K by 4K CCD with the uniform light source, and a 16-bit FITS output was there. So obviously the quality of the images were much superior. So first it was necessary to showcase the improvement which you can achieve, but from one 8-bit to 16-bit. So this particular paper essentially looked at that. So DS1 corresponds to this earlier 8-bit data series, and DS2 is the more improved new data series. As I indicated, again, beyond 22 cycle, this has been a problem, particularly for the last 20 years. Almost, Kodaikanal data has been very inferior quality as compared to earlier. So PSPT was used in this for comparison. So this is again is giving you this fraction of the plages in calcium, and there's a comparison with this. So this is the latest result I would say from Kodaikanal alone. But what is necessary is particularly for magnetic field reconstruction is photometric calibration, and that is what again Theo has done a detailed work. And in fact, now this is the composite series which I was referring to. This is the longest series which is available, taking data from all these different observatories. But I must point out again, Kodaikanal probably provides the the longest series. And in fact, the thing Theo has mentioned, this annual coverage of data set includes the KO as backbone. So Kodaikanal is actually providing the backbone for calcium series. Of course, you do have Mount Wilson as a pretty long consistent data series for this, but definitely Kodaikanal provides the longest of this. Particularly the earlier time, and as you know, the first 2 cycles of the last century was pretty weak as well. So that makes it very challenging as well to have a proper estimation. The other thing to be noted here is when you are able to really cross-calibrate all these different series and then produce this final composite, you see the duty cycle improves almost to 100%. So this is what is indicated here. Unfortunately, Kodaikanal is not available beyond, and that's why the duty cycle has reduced in terms of the calcium things, because we are more dependent on the PSPT, series at different locations, Rome or in the US front and all that. But the good thing is that the major part of the last century, we have a pretty good duty cycle in terms of the data availability in terms of the calcium reconstruction. So Theo has done this, and this is the photometric calibration, as I mentioned, is done. So the next will be the GSI reconstructions and so on. This is work in progress. But if you now look at the composite series for the large area, which will be also crucial in terms of the GSI reconstruction, and this is probably the state-of-the-art composite calcium large area series what we have. I would like to point out then, this is all about area or the locations where the maximum reflective proxies are there. The locations are also important. But the locations are all important. Then we realize that again from the Kodaikanal series, the timestamp is a very important issue because the north and south identification was done earlier by manually, and then again more recently Vibhuti has looked at it, with the big Theo. This is a problem which we were seeing, that when we produce a butterfly diagram from calcium large location, we find a lot of scatter. Of course, the 19th cycle is the most difficult cycle to always reproduce, but we find lots of errors. This is not real, obviously. And of course, the later cycles have much issues in terms of the data quality as well. What was the source of this? And the earlier thing, also what we realized that 1904 to 1906, this is the period over which no other data exists anywhere in the globe, but there were no timestamp. So how do you make all these corrections and so on? So this was a very detailed work which Vibhuti did. I will point out 2 interesting stories about this. The first part of the century, our people were recording it in IST. This is Indian Standard Time. Then post-independence, nobody knew India has followed a daylight saving time for 1 year, 3 years. And it was historically also not known. I never heard about it actually, because we don't have a different time zone as far as our lifetime goes. So this was almost like a discovery from the history that obviously you see a jump in of 1 hour here. And then for some reason or other, it was not recorded properly. People started using UTC. Obviously, there was and probably some of you are aware, India uses a half-hour time zone because effectively East and West is separated by 1 hour. But we don't want to have to, time zone to have a compromise, middle of the country somewhere in Allahabad. That timing was considered as a reference timing. So we are 5.5 hours ahead of GMT, universal time. So that corrections was also necessary. In fact, it's a type of observation which were responsible for this, wrong latitudinal stamp. This was what Vibhuti, realized that all these things were all incorrect because of the wrong timestamp Even you could see that there is an example what he has given way back here. This is pretty old, 1910 data, that the pole is marked here, but obviously it was wrong. You could see the plateaus here, so it should be somewhere there. So all these corrections were necessary. Otherwise, your butterfly diagram was not coming properly. So this is what I think Ruth is going to submit. I'm showing the results before he has even submitted for referring. So hopefully this we will see soon in accepted paper form. But this is the current butterfly diagram from Kodaikanal data alone. This was earlier, and as I said, few realized that there were problem it was not looking at, so we were not producing the butterfly diagram before. So now with all these corrections, we hope that the calcium series will be also updated. So what I'm trying to point out that it's not enough to have one series and then say, oh, we have done our job. It needs continuous improvement as well. So and hopefully we'll be able to do that. And for this further improvement, which we have now also realized that these sun charts also could provide additional input. It is in terms of the missing data and also, uniformity and so on. So this is, the digitization is still going on, but we have just published one paper. This is the, example of a sun chart. People have also used different colored pencils to identify different features. So again, these days, the youngsters only want to do everything automatically, of course. So we have done suggested RGB segregations, and then we have been able to just pick up those, filaments. So this is the, filament sort of 2-cycle results, just a snapshot I'm showing here. Very clearly, you see the poleward migration. This is the, important things which we need to have extract for all the, different data series as much as we can. Then this is the area series. You can have the length measurements, and you can also have a thing about the tilt. I indicated before also the tilt is a very important element in terms of the filament as well, because they are following the neutral line. And if we get or combine this information along with the photometrically correct calibrated calcium, hopefully we'll be getting into a better pseudo-magnetogram domain soon. This is just an update about again H alpha. My corrections are there on this thing. This week we are planning to submit. Theo is involved. So that's the area data coverage we have included. As you can see again, the Kodaikanal stands out in terms of its length of observation. Other interesting aspect of the Kodaikanal, I often indicate this to my colleagues, particularly in the West, that India being a poor country, we never changed anything. So we have been observing for the last 100 years with the same instrument, with the same filter and the same lens, and that makes the data most uniform. Because particularly in the Western world, people have upgraded the system, and when you upgrade, of course, you get a better quality of image. But to compare the earlier image with the upgraded system is a task, and that is not always linear. Whereas this makes it our process much easier. And as I indicated before, as far as H alpha is concerned, probably MEDO is the only data source which can really compare with the Kodaikanal series. So this is again done with the new digital CCD camera. We have two such system, and as you can see here, of course, as far as H alpha is concerned, we are also having much more ground-based coverage now. So this duty cycle is really getting better and better as with the current years. So here you see that the earlier phase we had probably H alpha, Kodaikanal and MEDO provides really the key element in terms of the poleward thing. Just very briefly, I want to indicate again here that when you look at the individual facility, whether it is a filtergram or a spectroheliogram, of course that makes a difference. The band passes makes a huge difference as well. Which layer of atmosphere we are looking at, is very, very crucially dependent on the central wavelength where these filters have been placed and the band passes as well, and whether these band passes have been consistent at the same location over the entire observing period. If not, then one should know, and that adequate corrections are necessary, and so on. So it is quite a bit of, I would say, rigorous work, and I'm very happy that Theo is really leading this effort of making this composite. Now, in this composite, what I'm just showing you the fractional area of H alpha, and the sunspot number is indicated by blue. So you can see pretty well that the fractional area is pretty well correlated with the solar cycle. But I would also highlight another thing which we are trying to look at is indicated here by the blue and the red line here. This corresponds to the polar, 70° to 90° filaments. And these filaments do have a direct link with the polar field, growth or decay. And also very clearly, you see that there is asymmetry in those. The timing is different. These have the direct linkages with the polarity reversal, the timing of the polarity reversal, and the growth rate of the polar field buildup, and the corresponding to the next cycle's initiation and all that. So I think this information is very, very crucial for all dynamo models, and along with the meridional circulation, kind of estimates. Probably these are the only, historical data sources which will allow you to even talk about, some of the flow things, because you can't make flow measurements for archival, 100-year-old data, but this will provide you certain numbers which can be comparable, and we know that that's very important. Here, this is the full disk H alpha from the composite. And again, you could very clearly see the poleward rush. And this pole rush is a very, very important element. Pole rush, whether we get it, a single pole rush or there are multiple, polar rush. This is whether it happens at the same time in the northern hemisphere to southern hemisphere. So there are lots of, I think, questions one can look at, and the dynamo theories, when they do reproduce the older data sets, they need this information. This is the final data series which I will be talking about in terms of prominence data. Again, you see that the data volume or data is pretty good in the earlier part, but it is deteriorates in the recent series. So prominence, again, since it is seen really in a high latitude, because this is the way it has been observed is by blocking the solar disk, it is allowing you to look at all the way to 90° almost. From H alpha, you won't get it because of the projection effects and so on. So this is again a very unique data. There's not much place such data exists. And if you fit in some things, you see very clearly that probably they are not linear as well. In the past, people have only placed linear migration rates, but very clearly we see that probably in the lower latitude, you have one kind of rate, and the higher latitude, it is much faster. So it's a second order, polynomial we have fitted. We produced some, numbers in terms of the poleward migration and the polar rush for different cycles, and we can very clearly see this rush is different. Now, again, as I indicated, that Kodaikanal data becomes, inferior beyond 1980s. So we have now included Meadow and Kanzerue. But interestingly, this is done was a little different way. Kanzerue and Meadow data, H alpha data was only taken. We blocked the solar disk artificially. Just image processing. We did the polar coordinate conversions and all that. The way the prominences were identified, same routine was applied to H alpha thing. So they're not apple to apple, but they do provide you with at least the location wise. See, we are not talking about, probably this is not comparable in terms of the size, because you don't see the same plasma when you look at calcium or in H alpha. But if you just want to get an information about in terms of the location of where these objects are, then this does provide you certain good comparison possibilities. So here you see very clearly that this does provide you good numbers. I did not include, there was another work was done by the NJIT group from Big Bear data for the polar, filaments, but they did everything manually. So it's only the colleagues from China can do it. So meticulously, they identified all the polar filaments, and they indicated that. So we have now a comparison of the polar rush from the manually detected polar filaments and this method, which sounds pretty good. Again, highlighting importance of the Carrington map from calcium H alpha. So this is an exercise which we did that for the period when you have MDI observations and calcium and H alpha observations from Kodaikanal, try to identify the polarity inversion lines and so on. I mean, it gives a confirmation from this kind of thing. But of course, at that time, this was again almost more than 5 years back, we were affected by lots of data gaps. Few days of data gaps will give you these strips at the Carrington map, but we have a much better, but we have to do this exercise again. I'm just saying that there is a huge potential. This is a work our Russian colleagues, Alexander led. He used our calcium Carrington maps and the H alpha Carrington maps. From the calcium data, he produced a calibration curve for quiet sun and the active sun differently, because the quiet sun and active sun doesn't behave the same way as far as the intensities. Of course, it doesn't follow a linear thing also, but if you more or less sort of agree with that kind of calibration, he could produce these magnetograms, particularly for first half of last century. What is to be, I would say, given a lot of importance is this again, poleward rushes here. What was identified also is this kind of odd rush, as you can see here, whether these are rogue active regions which you talk about. But basically, what we can very clearly see that these kind of, non-standard polar rush is responsible for double peak is one thing. There is also, other peaks in other phases of the solar cycle. It is not that, double peak comes just because of the asymmetry of the two hemispheres. We have shown, there was another paper from Vidya, even from our flux transport dynamo, we showed that the double peak can be achieved just by introducing this kind of, occasional, just for a few days, you have a opposite polarity, magnetic flux concentrations, which will sort of disturb the, polarity cancellations to some extent. So the point is that these kind of magnetograms are very, very important. There are efforts from different groups, and I do understand that the photometric calibration for the calcium is very, very crucial in this regard as well. So this is again an ongoing thing. But I would like to again just give a quick thing that if I now go back to my prominence, our prominence results, these are the poleward migrations, and if you just overlay on this, they match pretty well. So completely independent thing of the prominence data from calcium, what we produced, and this magnetogram, which is produced by Alexander, just based on the neutralized locations and the flux concentration in terms of the calcium. We don't have any. So I would take with a pinch of salt about the field strength here because of the calibration issues. But I think the location, the timing of the surges, and at the rate at which the surges are happening and all that can be pretty well be taken seriously. So just for last probably 5 minutes, I will talk about our new mission called Aditya. Why I'm just mentioning about Aditya is Aditya has 7 payloads. This talk is not for Aditya's because I need a completely separate talk, and I will not spend too much time on the different payloads, but I would like to highlight it has a combination of remote sensing and in situ. We are going to Lagrangian one point, so it is worthwhile to have a combination of multi-wavelength. We have a visible emission line coronagraph with the infrared capabilities as well. But what I would like to point out today in today's context is this instrument called SOOT, which has a solar ultraviolet imaging telescope, where for the first time we're going to look at near UV, 200 to 400 nanometer, continuously from space platform, and this has not been done. And now I will show why these spectral domain is very important. It's not the total solar irradiance, but I think the spectral irradiance has been given much more importance. And these wavelengths near UV has a much more impact on our climate than other wavelengths. So, so in that context, I will say a few things. Just a current status update. We are still hoping that we will be launching soon. 23rd is our landing date scheduled for landing in the moon. So I hope after that, we will be, tentatively it is 26th August now as the date of this launch. Fingers crossed. Here, I'm just trying to highlight that if you look at a solar dark body spectrum, of course, the TSI is mostly dominated by optical, but you see the variations in the near UV. And that makes any instrument to build also more challenging, because you have to have a camera. If you have only possibility of taking one camera, which can take care about the flux changes of this magnitude. So you have several orders of magnitude, contrast required of the dynamic range required for the instrument. We have 11 filters. Some are, basically covering from photosphere to chromosphere. I want to again just point out that we have the calcium. So probably we'll have a possibility of continuing our calcium observation, which I've been doing from Kodaikanal for the past 100 years. And this place will give us a new vantage point. We have magnesium line, and we have magnesium observations at the line center and also in the wings and so on, so that it provides a different thing. It will be quite an interesting thing. I don't have time to go to it. Now people are talking about producing irradiance measurements from magnesium as well. It is a good, and there is a lot of work which comparing results from calcium and magnesium. It appears it is very well correlated. So since magnesium observations are going to be there for near future, whether we could use the magnesium observation for continuity of the ground-based, all these archival data. So in that context only, I thought I will highlight today that we have these chromospheric lines, and we'll take synoptic observation because this is full disk, and we'll have possibility of synoptic programs and observations in certain chromospheric lines, apart from other irradiance measurements in this. So I will probably skip all the science objectives of the suit. As you can imagine, there are multiple observations, multiple line observations available near simultaneous. So there is a strong possibility of some climate studies here, because these are the spectral particular windows with a wider passband, which affects our atmospheric layers much more. Of course, there is also a group, I will be also part of that, to focus on prominence studies. And since we are going in space, again, apart from the prominence, short-term variability, that's again one ball game. But whether you want to prepare catalogs for prominences for, say, one solar cycle, and compare with other earlier prominence results, because here we will have much better spatial resolutions and so on. This is again a 4K by 4K sensitivity with 0.7 arc-second pixel. So there is prospects of continuing some of the long-term studies what we have been doing from the ground on this space platform also. So that was my intention of showing this. Again, this is the spectral irradiance measurements as I mentioned, and there are indications that with the solar cycle, it appears that the spectral irradiance variation could be as high as 20 to 30%. It's not the TSI. I'm talking about particular windows of spectral irradiance variation, and there are models which is predicting that the 20 to 30% variability could be there with the solar cycle, and that will have a much bigger impact on our climate because of the wavelength region which we are talking about, and this has been completely unexplored so far. So there's some new elements in terms of this. As I indicated, we do have lots of younger people in India, And this is a support cell I advertise because we are hosting it at Aries. And we are trying to train all these people through this support cell. We have periodical workshops and all that. If there are people in the audience want to participate in any of our workshops, at least there are 4 or 5 workshops in a year, apart from short visits and all that at the Aries for the training purpose. So again, I will highlight unique opportunity of multi-wavelength study from historical data, because I think I have seen in the past that people have spent their whole life with only calcium, or people have spent their whole life with white light, but same individuals have not looked at all the wavelengths together. And I think if you look do that, then I think it has a complementary, additional information can be gathered. I have to acknowledge that, this is a big team effort. This effort started by Professor Jagdev Singh many years back, and I was handed over. I had no clue about the long-term study, but I was handed over after Professor Singh's retirement, which is again more than 10 years now. And thankfully, I had lots of good students. They were only interested to do work on space data, though, I must point out. But somehow the quality of the data, and since I was also trying to pick up or learn about long-term, physics, so some of them are here. You see, this is the place where I come from. Beautiful place. So you're most welcome to visit me. And this is my current, group of people. One more faculty who has joined. So in fact, in my previous group, I had only one woman student, and my wife was always complaining that you don't take enough women students. So now I think I have made some corrections. I am very proud of my students, and thank you for your attention.
Thank you so much, Kodaikanal. All right, I know we're going to have some questions. So who would like to ask the question? Raise your hand if you're online with a question. All right, first, go ahead.
Yeah, I was wondering with the flows on, can you go to the butterfly diagram?
Butterfly diagram, okay. I have few butterfly diagrams, so which one you want? The first one, okay. First one, from the sunspot, you don't see the high latitude. That's limitations of always sunspot.
Okay.
Yeah, okay.
So when we see here the emergence of the active region, do you have an observation about the large scale motion of on the sunspots? What looks like they are contributing to the magnetogram?
Yeah, it's a good point. And in fact, we were discussing about these elements in the morning as well in our ILWST meeting. Unfortunately, see, the Dopplergrams are not available for historical data, right? So the flow measurements of these sort of, time scales, because these are one image per day kind of thing. So you only see the appearance of the active regions and you follow these active regions, but simultaneous flow measurements are not there. But flows do have an important role to play in their life, existence and their lifetime and so on. So this is a work which is only possible from the space, data time, because now, of course, COM can also probably provide some insight, because you need the flow measurements. The flow measurements are not there for historical data. I mean, historical time scales, I would say. Yeah. So this is, I would say, still nobody has looked at, and as I indicated very briefly, we have now started to look at different kind of bipolar magnetic regions. Those who are living long, say full disk passage, or they're living, say, for a few days, in contrast to people, things which are living only for, say, a few hours. And it appears they really behave differently. And they behave differently. One is because they're probably not coming from very deep interior. That's our probably guess, I would say. And also because of the flow. The region where they're coming from, I mean, rather they're emerging at, it's the flow patterns in that location is also very important, which nobody has looked at so far. there's no comprehensive result of that apart from isolated observations, I will put it that, part of this kind of statistical work.
There's a question from Jana Kausman online.
Yeah, I think Jana's.
Hi, Dipankar.
Hi.
Thank you for the talk. It was very interesting. Could you speak to the flare observations with the ultraviolet? I don't know how to pronounce it. Sweet.
Okay. Sweet. Yeah.
In particular, I tell you why, because I think this is the only instrument that I know of that had both sides of the Balmer continuum. And for flares, that apparently will be a very, very interesting diagnostic. So I don't know, what kind of cadence you have, how you trigger a flare trigger, or the resolution, and so on.
Yeah, thank you for asking this question. And I think this has been realized that the flare, so we have a auto flare detection algorithm on board. And at that point of time, we can do a smaller field of view observation as well. 500 by 500, I think that's a smaller, I don't remember the precise number, because it's a 4K by 4K CCD, full disk, it goes slightly beyond, solar disk as well. But during the flare and the flare trigger, there is a auto, software inbuilt on board, and that will allow you to take, and that you can choose a particular, we are planning to do it in magnesium, but it can be programmed to other filters also. So this is, it is already in the plan to have a very specific flare mode observation. And since you asked this question, in fact, we have on board flare trigger flag from suit instrument back to the two X-ray spectrometers, and vice versa. So we have some threshold set up in the two X-ray spectrometers. The X-ray spectrometers, the Solex and Helios, one is working in 1 to 30 kV, the other one 10 to 300 kV. And they have particular thresholds given on them. And that will actually put a signal back to the suit instrument to have a flare mode trigger. So both sides, it is there.
Yeah. So you plan to do just a single wavelength to go faster, or do you plan to still cycle through, say, a couple, 2 or 3 filters?
Yeah. So the plan is to do it in a single because we have only one detector.
Yeah.
To go for a faster cadence, smaller field of view with one filter.
Right. So maybe we should discuss, some other alternatives to that.
Of course, because these are observatory class mission, and that's the idea that you exploit as many ways. You can have different modes of observation. So only issue is because we don't have all the time the telemetry. So it has to be, as you know, for Lagrangian one mission, we have to otherwise upload everything at least 1 day in advance. So if you know that this is the time you expect the flare to be, and then you can have a set of observation plan the way you want. But as I indicated, we have 11 filters on 2 filter wheels, and with the combinations, each filter wheel can accommodate 7 because I think there are some open and for other blocking it and so on. And it is possible to use multiple filters also and have a sequence, but there will be near simultaneous measurement, not simultaneous, because we have only one camera.
Of course, yes. Okay, thank you.
Other questions? I have a question about the archive, the data. So you've got all these wonderful different simultaneous wavelengths and measurements and types of measurements and prominence and filaments and so on. So you're probably serving a bunch of fits, or can you tell us a little bit more about the nature of the data and how it can be used and, for instance, searched for different types of structures?
Yeah. So as far as the archive is concerned, there is no interactive that kind of graphical platform we could develop. We are only allowing you to search the data about its availability and the quality. So there are thumbnail images, and you can get and then you request for the some volume of data, or if the volume is too large, you just send me email. We'll arrange to put it in majority of the people who are really working a lot with the data we have just copied it in the hard disk and, just posted it. So that's, then you have the entire, tens of terabytes of data with your thing. So I think individually you have to look at your interest and then work on this. So if you want, we can provide you. Essentially, majority of the people are taking the, the first level calibrated data, which has only calibrations of rotations and the flats and so on. But extracting the information and so on and so forth, we're leaving it with the individual. Having said that, whatever data outputs, like, if you now publish anything in the FJ or any other equivalent journals, they're asking you for the output also. So we are publishing the output as well. So like the sunspot area cities, butterfly diagram, all the data is in the public domain. So we are actually, the last one is in the GitHub and then, the CDS and all that have to be, we have, put that. Carrington maps. So the Carrington maps, some of, all the earlier Carrington maps, because FJ wanted that. So now, there is another thing, FJ, supplement series also asks for your data output. So in terms of the data outputs, some of the data products we can provide you, which we have extracted. But it again depends on, other group members, those who are using the data, whether they want to share their data products. But from our group, you ask for any data products, we'll be happy to share with you. Some of it is already published with the publication itself. As example, I was saying about the Carrington map, because this Russian group, they contacted me, I had no clue. Then they said, you just work with the, thing, but then Vidya got involved. So we were looking at, possible dynamo explanations, about the double peak nature, double reversals. It's not one single reversal, but, there is now possibility of a multiple reversal within one particular cycle. So those kind of elements now we are looking at by, sharing the data as well with others. Yeah.
Okay, I get it. So basically the archival data is essentially the digitized images.
Right.
Got it.
Yeah.
But there's stuff that's been pulled out, like the locations and so on and so forth, which you published already, and that data is available online through the journal or by contacting you.
Right.
Got it. Yeah.
Because there are many people, they are only interested to work on the series output. They're not interested in extracting how you have identified the filaments. So you give me the filament sizes, you give me the filament locations or their areas or the tilt. So these are data products, I would say. We are going to make available as and when, we extract more. So whatever is published is already there.
Yeah. So like, for example, for the sunspot, we have only masks.
Yeah.
And those images are not public. So, but someone request, we can provide them.
Okay.
So like all the parameters extracted from the mask is available to the public right now. But if you want mask, you want to do your own analysis, something like that. You need mask. You don't want to detect the sunspot from the event, then you have to ask. And then we can provide it.
Yeah, same with the plugins also. The plugins have been identified that the masks are there. So binary maps are there, maps are there. So if somebody, really understands the things, how it works and all that, we are free to, happy to share those images as well. But they're not in the, website, because not many people will understand also.
And data volume as well.
Also, it's just terabytes. Whatever you talk about, it's terabytes. So.
Oh gosh, yeah. Alan, is that?
Am I understanding correctly that on some particular times you actually labeled features and you have those labels with locations, names, and so on?
Yeah. Yes.
Then I strongly suggest you look into a self-supervised machine learning to
Yes.
run the entire data.
Absolutely.
Because then you will have it all.
Yes.
If you have that thing to start with, it's a shame not to do it.
Absolutely. So as you mentioned, all the younger students, if somebody I have to attract, I have to tell them that, please use the machine and improve this. So you have already a training thing. See, as we said, the binary maps we have. So the binary maps provide you the training data set in any case. So then you, train the machine, and then, supervise, unsupervised, whatever is your choice, you make a progress in that way. In fact, the sun chart data for things which we are doing is only with all machine. So machine learning only. Nobody is going to do any other first. It's not possible also.
Other questions?
Well, what about like if the sunspots emerge at high latitude and another sunspot emerge at low latitude? What is their contribution to rush to the pole?
So essentially, it is believed, again, as I said, historical data, people have not tracked individual sunspot pair. That process has not been, so we have started doing that, but again, for that, you need magnetic information also, and ideally, it is possible to do from a magnetogram. So we are doing that now with the magnetograms. But the historical data, it's not done. But so it goes by the standard thing that, high latitude things only contribute to the polar field. So that is generally seen also from the timing of the anything, if not, even the calcium stuff and all that, not this one, but probably the H alpha will have. Yeah. So from the timings and all that, you can make out roughly that, when does this polar rush thing really is more sort of significant. From the width of this stuff, you can make out. And then that will provide you also linkages with which sunspots are or which active regions are coming to the high latitude. So here you can see very clearly there is a link here. The strips do start at certain phase of the solar cycle, right? It doesn't happen all the time. Having said that, if I now look at the, this one, there are all these odd guys also. So here, of course, during this period, you see the surges have started happening and all that. This guy also there is a surge, right? Not probably this one. So the lowest, sunspot in the minimum phase and all that probably do not contribute that much. But up to, of course, the middle of this cycle, there is a contribution to the polar buildup. So this gives you some indication.
All right. Maybe.
Yeah, sure, exactly.
Yeah, exactly. So I think we can wrap up the colloquium. We may keep you and ask you more questions. But
Sure.
thank you, everybody online, for coming. And thank you again to Pankar.
Thank you.